Okay, we want to talk a little bit about friction force. We have a new equation that we want to introduce here. When we draw the friction force vector onto our FBDs, we can calculate it very simply. The friction force is the product of two things. The first thing is a Greek symbol called mu, and the other thing is one of our other forces in our FBD. It's the normal force. So you know how to draw the normal force with the surface pushing up perpendicular. When you have an object, you have the force of gravity, and then you might have the normal force pushing up like this. So you're going to need to calculate that so that you can, because that's part of friction. So you're going to take the normal force times mu. This is mu, the Greek symbol mu. What is mu? Mu stands for the coefficient of friction. Okay, it's not friction. It's called the coefficient of friction. Sometimes people start thinking, if I ask for friction, you're trying to think for this. No, you're trying to find friction, which means you need to find mu and multiply it by the normal force. This is the equation to find friction. The coefficient of friction is basically what are the surfaces that are rubbing together. And you just have to look it up in some handbook. If I had rubber tires on dry pavement, or maybe rubber tires on wet pavement, or rubber tires on ice, there's a whole bunch of coefficient of frictions that physicists have calculated and put into some book somewhere. So this number here, it's a number, it's a coefficient. It doesn't actually even have a label. It's always going to be like point something, like 0.37 is mu. The reason it doesn't have a label is because if you solve for mu, it's the ratio of the friction over the normal force. Both of these are in newtons, right? So if you take Newton divided by Newton, it cancels out. There is no unit for the coefficient of friction. It's just a number that describes kind of the two surfaces that are sliding past each other. And so you're going to either have to calculate mu, or I'm just going to say, the coefficient of friction between leather and vinyl is this number. And then so you'll be able to use it when you're calculating some friction problems. One thing I want to point out here real quick is there's actually kind of two different kinds of mu's. There's mu s, and then there's mu k. This stands for static coefficient of friction. This is kinetic coefficient of friction. And the key here is it's interesting. If you take a box and you put a force meter on it and you try to start pulling, and wait until the thing starts to move, you can calculate a coefficient of friction, but that would be using the static coefficient of friction. This is the coefficient of friction that happens right before it starts to move. But once you start pulling it along at a constant velocity, you have actually a different coefficient of friction. The mu static is always bigger than the mu kinetic. There's kind of some interactions on, like, if you have an object and if you look on the microscopic level, it's not perfectly flat. There's all kinds of little imperfections, and while this thing is not moving, these things kind of hold on to each other and bond together a little bit tighter. So it takes a little bit more force to get it to start moving, and once it starts moving, then it can easily kind of move along. So the kinetic mu is actually lower than what the static mu is. It's kind of like in chemistry when you had to put in a little bit of heat, a little bit of activation energy so that the whole reaction could go. It's kind of the same thing. You need a kind of a little bit higher mu to overcome, and once you're going, you'll have a little lower, slightly lower kinetic mu, a kinetic coefficient of friction. Basically, this is the one we're going to use in all of our problems, because we're talking about basically the problems all kind of moving along. So I won't designate the difference between them, but I kind of wanted you to know the difference. So this is our equation for friction, and we're going to use it in the next, pretty much all the rest of the problems.